Hey everyone, as always we will talk in English. Thank you for no, I'm here. So I'm right now located in RTU Riga. We have some people in attendance, but like other times when I come to Riga, please come to the auditorium. You say you're not hearing something. That's weird. Okay, let's check again. Can you hear and see now? Plus minus. If not, we'll try to find out what's wrong here. Let's wait a little bit. Okay, here. Yeah, you can leave some likes because these are public videos, so I will get some traffic from other students as well. I already saw some students that are not from our university joining. Yep. Sorry, I was running, but just a second. I have an exciting topic today. Hope I will be able to speak. Yeah, I was not expecting that. Okay, hopefully you will be able to speak. Again, so we have different groups of students. We'll start with the homework, then go with the today's session, and then check some other aspects. But the main thing is that next week and week after, probably I will be in Dubai, so probably will not be able to do this on live, but like in person. But we'll try to do this live. As I said, as I myself, maybe I mentioned in the first section, first lecture, but I'm running a couple of AI companies, so it's not being able to always be in person, but I will try to be again in person in Riga. So I met Thomas here, Thomas, right? Yeah. So then hopefully please come other people that are from Riga to actual location, and then I will be also maybe sometime in RTU Liepāja. But again, so this depends on yourself. If you're not active in the course, then I guess there will be a second chance to join this dummy course that I will make later, which will be for business people. But if you actually want to earn money with AI, then you probably should be able to complete my course here. So hopefully my throat will start working. Anyway, let's look at the previous homework and then then move on to today's lecture. Okay, the best way how to do this probably would be with the full screen because we have some rendering stuff going on there. If any questions, problems, try to write me an email. We'll probably not be able to respond quickly, but we'll try to respond as soon as possible. Also, if you write here in the chat now, we give some examples, we can solve it together. So, okay, let's look. So the task was to create a 3-element robot arm. Okay, and this is working nicely. At least let's see with the equations. So this is one of the examples. Šausmas. But yeah, you see something strange is going on there. It should not be like that. Okay, let's look for some other examples, and the basically if by any chance I will not find good examples, we can fix existing examples, and we'll definitely look at the equations together. So let's see, let's try to run another example. Okay, right, so this looks nice. Okay, so now it's reaching. It should become straight line. And the idea is here that if I would have absolute error, then this would work the same speed as in any place. So if I put large distance here, if you see it immediately starts working very fast and then very slow, right? So this is because, as you remember, the curve of the loss function for squared error is when it comes closer to the target, it goes slower. But we'll see. So this looks nice. Let's look at the equations. Okay, let's examine at least 2 examples, maybe more. Okay. So theta's rotation matrix again in the Numpy Python. Even though you can write it like that, it's better always to do this. Make it more readable. And also, maybe that's not optimal to put mathematical operations in return. In return, this will make it big problems for you later, even though you think you're smart of making one-liners. I've never seen that one-liners is a good option for programming. It always is a bad option. But the example of this was really nice. We'll also look just in the penalty for the crossing ground. It seems that somebody implemented that as well, so this is beautiful. But also, if you see cosine, sine repeating, probably you would use some kind of temporary variables to not repeat it yourself. So something like that. But again, I'm just giving you some code review comments here. So that's that. Then absolute. So the squared error. So the additional penalty, we'll look how this is implemented, so what it means. So there's a points, absolute value, so this means how far it is from the ground. Larger penalty, larger violation. So the second dimension is y. If I would write this, I would probably not do it in this way, but as I told you, this is not readable code. The better would be something like xy equals point or something along these lines, and maybe this would work probably, or whatever, like this, and then y, right, like that, and this would be more readable. Again, as a rule of thumb, if any programming project you work, if you start writing something with the squared brackets, probably wrong way. So that's that. So calculate gradient. Okay. So I like that this person has splitted the code in some kind of logical segments. So it's nice that we see that person like thought about this problem. Okay, that's good point. Okay, so rotation by the length of the arm. So it is moved by the initial position, which is not passed as a parameter, which is strange, but fine. Then rotation of theta's. Wow, never seen this kind of implementation. Okay, this is definitely not conventional way how to do this, but nice. So basically, the person summed together theta's here and then did the rotation matrix. What I encouraged you was to use the chain rule and to have multiple rotations, but you already have multiple rotations. But why you have multiple theta's? That seems super duper strange. Why would you have multiple? Well, so I'm just looking. I'm for sure that you can solve this without having to sum theta's. That is very strange. Very strange. So the equations looks right. So these equations are correct, but the thing which is not really correct is that you would need to have theta 1, theta 2, and theta 3 like that. So that's for sure. Like why did you plus it there? I don't get it. Probably because there is something really fun about derivable mathematics. So any equation that you can calculate derivative to, you can probably optimize. So the funny thing is that even though this was not correct, maybe it just worked because you were able to optimize. We will look at that. So penalty of points, penalty loss. Okay. So, okay, for the total loss, that's fine, but penalty must be added also to the derivative. So let's look at that. Rotated, what is this? So what are the gradients, right? Gradients, where's the gradients themselves? Okay, grad, where are you? Okay. Loss, epsilon, constant, MSL, loss. This looks strange. Where is the rotation matrix derivative? Yeah, so this doesn't look right. Okay, I even want to have here a meme somewhere. I had the meme. Just a second. So this is really deserving a meme. I had it prepared for the last time, but last time a few made really nice examples of code. And I did not need to use it, but this time this deserves definitely this. So basically, this is your code looks crazy, but it works basically. So it's definitely not the mathematical way how this should work, but as you saw, it was really nice. So that's fun actually. So, but yeah, I would definitely give points to that person. So it's really good attempt, right? But definitely not the way how this should be calculated. It should be calculated using derivatives, proper derivatives, which were not implemented there. At least I did not see them for the rotation matrices. But no worries, we will. It is way better to actually do these things rather than not do them. By the way, I've seen that a lot of students have similar code, which means that you copy it between each other and made the same mistakes. So which is not cool at all. Let me share the code in a second. I'm just trying to find anyone who tried to do this properly. So a lot of same code copies, which is really weird. So it's always fun to see if some students want to share their code in between themselves. When they share the wrong code with themselves, that's super easy to see that this is totally copied. So at least this person, even if did not share the code, then somebody shared or something, because the same wrong equation was many times published. So I found this example from some student. We'll see if how this works. So this might be the correct way. We'll see. Let's see. Okay, it seems to be working as expected. And at least here I see what I was looking for. So I have rotation and derivative of rotation. So this is a good start. We are doing something right here. So and then you see, compared to the previous student, how simple it is. Basically, what I'm asking you is super simple. It's not some kind of complicated Frankenstein code. So here is the the derivative of the third one. So this is, let's go through, see. So this is the inner state, outer, so this is the second segment, third segment. Seems about nice and right. By the way, just to keep notice that what you see here, this is a, so this is plus here, plus, so it means that basically what is the last segment? The last segment is actually this guy plus this guy plus this guy, right? And if you have this whole equation, then it's become super easy to derive, because if you look at it, this is like the simplest calculus equation to derive, because there is just multiplication or dot product and plus, there is nothing else there. So basically this should be a very simple task. We'll see. So that's let's keep this so that I can fix it if necessary. So this is the last segment, this is the second segment, P3, whatever. So I'm just writing it for myself. So let's see the thetas. So thetas are, so there's something strange here as well. Why d theta 1 is real, so this is something weird. Well, maybe let's check. Right, so d theta 1. Okay, oh, right. This is cool. I was, so yeah, no, this is cool. So this is the whole equation with regards to the loss. So this is right. So so I don't need actually the other one. So DR1, this is good. This is good, right, I hope. Wait. Something is not right here. Again, so so loss with regards to the loss, right? So this is the chain rule. This is right. Again, I will try to quickly fix this, but again, this is typical thing of deep learning and machine learning. I think the Andrew Karpathy, who was this Tesla AI director, once said that deep learning fails silently. So basically, you think everything works, but it doesn't work. So basically, there is some things which I see are not correct. So I believe that it should be actually something like plus dr. Well, so I will check. You know, like we'll see if my changes make sense. if you think I'm making mistakes, then please point out to me. You know, like I had a long work day, so I might do something stupid here. We'll see. So I believe this is like that, right? And then yeah, so definitely there was a mistake there, but it worked. So again, this is the typical thing. It sometimes works, even though it should not work, and it's definitely not the way how it works. So we'll see. So so the next step, data 2. So dr. Okay, let's just what we could do. So this will be. I will just copy some stuff of this because don't want to spend time on this. So okay, so this will be r dr. Basically, you just need to change a couple of these and that's it, and not understand where is the problem here. So and this last one looks right. Okay, so this solution was much closer to the reality. We'll see if it works. Run. Okay, it works, but then also also the loss of the so the azimuth, right? So the ground. If I don't want, whoa, there was okay. I clicked outside the boundaries, but if I don't want the arm to cross itself or go down the the below the ground, then probably the way how to achieve this would be so how to achieve would be this. So I will not do the whole calculation, otherwise it will take forever, but basically how to achieve is something along the lines of k. So this is like the middle point, for example. So if the k, so what we want to have is a k k1. So this is what I showed you before, not correct, but bear with me. So this is y dimension, yeah, and if I put in the loss in the front, for example, minus, right? So, and I would add this is the loss of k, and then I would plus it here, and then I would calculate the d loss of k, right? This would achieve the desired result. So I can add additional losses along my whole functional graph at any point and achieve the result so that it doesn't want to go under the y-axis 0. So basically, and how I achieve this in this case is I'm just using the same mean square. So yeah, there's actually no need for mean, but basically the same squared error, and not minimizing it but maximizing it. Like just add minus it, maximize. So this would be the way how to solve these things. So I will put this on the Jamboard, and let's move on to today's session. So the the more you will do these things, the more comfortable you will become with them. And at the end, you will be able to implement papers that 99% of the world don't know how to implement. They just copy GitHub and make stupid stuff. So it is like that is the actual reality. And I can attest to that 100%. Currently, I have a couple of master students who's writing the research on deep learning. What they are doing, it's like if I would do the same paper 5 years ago, it would be much harder to compete with other students around the world. But because we have nowadays the generative AI, ChatGPT, and all of those, there's like a huge layer of really bad papers, like the stupid prompt engineering ideas, which is basically even they start to publish, even Google DeepMind publish papers without any kind of mathematical proof, just like I made this prompt, did that thing, and even don't quantize what is the quality of those methods. So it's, if you finish this course properly, you'll be able to publish cool work basically, because other people are publishing really bad work nowadays. So I mean the good work is something that will withstand, you know, you will get proper attention for that work. So it's not like that it's meaningless. So okay, let's keep digging in today's. So I think today's session will be also quite fun and very practical. We'll try to build our first artificial neural network by hand, each equation by each equation. So, but before that, let me visually show you what we're gonna do. So, if any, let me check also in the chat. Okay. So again, there's somebody asking on the chat about the grading. So if you submit work which is not copied from the other student because it's useless, especially if you submit before the next lecture, that is super valuable because we can learn. If you submit, I will grade it, except if it's like just empty or copied from the student, I will give a proper grade. If I find that this is a copy or refactor or some other dumb approaches, then I will give 0. But then at the end, we will have the exam. Exam will be the main thing. So because nowadays I'm not stupid. There is a cursor, there is the GitHub Copilot, right? So I believe some of you already using those for the homeworks and not learning anything. So that's not optimal way how to do this. So please try to do this yourself. Try to learn yourself, because you're not trying to cheat your way into some good work positions. You're trying to be the best in this field. Otherwise, some other guy with GitHub Copilot will take your place, basically. So anyway, so here is the TensorFlow visualization. So just for you to know, in let's say 2 lectures maybe, we will start using PyTorch, which is the basis of all deep learning nowadays. Some, like, let's say 5 years ago, TensorFlow, Keras was something like that. Nowadays they're out of business basically. So, but this is still nice visualization. So what we have here, there is the inputs x, two inputs. So we will have today actually the prediction of the car prices from the classifieds. We could also predict, I don't know, any kind of things. But basically here would be, let's say, how old is the car, and maybe maybe let's say what else there was. So what is the odometer, kilometers, whatever, some data. There could be many data points. You could add as many data points as you want. And then at the end, so let me have discrete output. So let's say blue means buy, red means don't buy, right? So, and then you create your fantastic neural network of any layers you want. So the typical way how this works is, especially if we're talking about the image classifiers, we have 8K image, some kind of huge image, and we're trying to neurally compress it down to to 2 classes. So this is like a compression, like artificial neural network compression. But in case, if you have very little features, I think last time I already mentioned you that you can project in higher dimensions. So you can have high dimensional data project in the 2 dimensions, like these points. So each point would be car, for example, and then we need to know which car we buy, which we don't buy. So we can project in 2D, but we can also project in higher dimensions and then project back in lower dimensions. So there is a lot of dimensionality laws and theory around it. So we can discuss it about this later. But just this is important feature of the dot product. Last time I showed you that I can take 2D vector, project it in 3D, 3D in 2D, and do all sorts of those things just using the dot product. So, and here's the same thing. Okay, great. So if we try to optimize this thing, so normally, if I would just add multiple linear layers, which I have, maybe I have it here. So, so this is input features, hidden state, and this is the matrix multiplications, output features. So if I have just a linear layers, then this is actually kind of important. Then it will do this, basically. It will try to project linearly. So maybe let me add some more equations so we have more sense of what we are doing here. Maybe I should also start using the LaTeX. So I, again, highly recommend anyone ever want to do some proper science, learn how to do LaTeX. I think there's also web editors. If you find some good web editors, let me know where to find them. But because just to share other students. So okay, let me start building some model which we could build together. So let's see. I actually have some template which we will elaborate more. Right, wait, it's not copy. Okay, cool. So chicks, okay, right. So yeah, so there will be, so in there's a 10H. This, should I really have to have 10H? Let me see. Not, we could actually do this. Okay, maybe let's use sigmoid. Wow, why did I made this kind of equation, really? So 10H also works. We will talk about non-linearity just in a second. No worries, I'm just a little bit confused myself why I gave this equation. Okay, let's use something simple. Okay, so if I have linear, please don't write it yet. I mean, just if you want to practice LaTeX, you can do this, but let me explain a little bit. So first of all, whatever you see functions, so these are mathematical functions, not the programming functions, right? So wherever you see the x, y, whatever, some variables, never assume that those are like actual variables in programming language, because what it actually is, c dot, they are like a placeholders, right? So if you see w1, w2, those are the actual variables. So linear x, wb, these are just the placeholder variables, right? And then here you see linear layer, right? And linear layer, what it is actually, so linear layer is linear projection, and this is actually fundamentally interesting. So because this equation is why NVIDIA is a $6 trillion company, because this equation is the same equation we used in the computer game, right? And this is the affine transformation, or in other words, rotation plus translation, the same equation that is being used for like 50, 60 years in every computer game. So NVIDIA initially started to optimize this equation running for the triangle rendering on the screen. And then it turns out that the same equation is exactly for the artificial neural networks. So this explains that part. So, and what I'm trying to show you here, so this would be three-layer neural network, in quote unquote. We will see why it is not really that. So copy JPEG, and there are a couple of points trying to get to you. If you have questions, please write in the chat. So so what it is here. So I have this equation here. Let me pull it up, and also some visual. So where is my visual stuff? I had it somewhere. Yeah, here. So, and this is actually the same situation as in that playground here. So if I have just the linear projections, which I have in this case, which are these guys, then you need to imagine that I'm trying to project these points. So ignore this part now, but if I'm trying to imagine that this input is projected in each linear layer in different way. So in the second linear layer, maybe this will be ordered out, like it will be projected on this line. So there will be some reds, some greens, some reds. In the next linear layer, it will be projected, let's here, next one here. But the funny thing is, if you followed me, the next one here, the next one here, it will be projected at the end towards the same line that is the last line, basically. So in other words, I can draw 10 lines, or I can just draw, imagine if I don't have any of these lines. So let's do this. So I'm projecting first layer, second layer, so the points are traveling from here to here to here, right, to here, right? And now I'm projecting just with the one last layer with this linear projection. The same thing, basically. I don't care about 100 linear layers before or just one last linear layer. That's the same thing. It's just like super inefficient method, but it will be projected to the last linear layer. And that's why here also it doesn't care about all of these guys, so these are meaningless. I can just delete them basically. It will just project to these last two basically. All right, but that's short. So it'll project these last two layers, so the last layers. So but when we introduce the nonlinearity like sigmoid here, and restart the same simulation. But I encourage you to play around with this when you have time. So the playground, TensorFlow, whatever. So if I run it again, let's see if maybe I made it too complicated. That's funny. It doesn't work. It should be working. So let me see. Let me remove some layers. Not add, but remove. Okay, let's run again. Right. Restart. Run again. Okay, now it starts working. So again, if there is so many things to cover, but basically the neural networks sometimes also can start behaving not as good when you have too many layers, but but there's something definitely not cool. Let me try it again with 10H. Okay, with 10H it works nicely. So regardless, I can try to make it work. So any of you could try to make it work with Sigmoid as well, because Sigmoid works and Relu works. So the Relu is another, which we will look at later. So this looks like that, right? So this is really very dumb nonlinearity, but basically any of these work. So some needs a little bit of hyperparameter tuning, which we could actually do. So Sigmoid didn't work previously. We could try to make larger learning rate, whatever. So let's see. So yeah, with larger learning rate, it also works. So what I just did is something that is called hyperparameter optimization. And this is also one thing that 90% of do-it-yourself GitHubbers do not understand, that you cannot take AI model, press train, and hope that this will be the best result. You're just like missing out on, let's say, huge improvement. So the hyperparameter search, that is a specific area we will cover as well. So I will look also in the chat if you have some questions more. So definitely, okay, so I'm not, I guess, not as exciting stuff right now. I have just 2 likes. Maybe I'll earn something more, right? So anyway, so but I like it. So if you don't like it, then you can join this dummy course later as well. But this is really cool stuff actually. So let me see. So if I'm now looking at this thing, so now what you need to imagine, what's happening actually, is that the nonlinearities is pulling out the data in some hyper dimension, and then you cut it, and then it again pulls out, cut it, pulls out, and this is super powerful technique of basically separating and training almost anything. So let me show it here. So this will be sigmoid. So let's add some sigmoids here. Sigma. Right. Let me add this thing. So it should be after any. So this is how the sigmoid looks, and and this should be after any linear layer, right? But also let me make it a little bit simpler. Right? So that with the 3 layers, this will take a lot of time as for today. I just want to make it quickly to some good results. Let me try to, so we'll definitely cut it down. So I had some image where I had to cut it down. So how many layers? Like I said, 2. Okay, let's leave just 1 sigmoid. So so let's delete B. Okay, like these things. So these will be deleted, gone. So W, I don't want to miss some brackets, but probably I gonna. So, okay, let's see how it looks. Looks better, hopefully. If I'm missing any brackets or making something stupid here, let me know. It seems actually that I am, because sigmoid, definitely am, because there should not be here. So sigma must be around that thing. So there is linear bracket, sigma bracket. There's too many brackets for sure. So let's see. So linear bracket is, sigma bracket is, linear bracket is. So this would be the simplest possible artificial neural network that is possible. And the sigmoid. Let's talk about sigmoid, and then let's start to building some stuff. So the sigmoid itself looks like that, right? So like that, and this is a exponential function, non-linear function, and let me show you how it looks like visually. So, and this would be, so this will not use, this is stupid, but I'm just showing you that because I literally have had master students who are so smart of building linear model layers on top of linear layers in their master thesis. So that's really genius. So here is this thing, and here is the sigmoids. So this is the sigmoid. So yeah, the x. So yeah, the x-axis is the input and y-axis the output. So it's always will be from 0 to 1, and if it's not like a straight line, it will start giving you this nice effect, which will give huge good properties. So this will produce that. So okay, so that's that. Okay. So if something not clear so far, definitely write some questions in the chat. So is the video already working? So nobody is asking anything me. Okay. Anyway, so let's move on. So the next part would be ss.lv. So if none, can we make it English? The only Russian, great. So this is the classified in Latvian. So there you can buy cars, right? Used cars. Unfortunately, only Russian, not English. If it would be English, then I can show you. Maybe what happens if I just write here English and it actually works. Funny. No English. They didn't add the button for English, but it works. So let me see, which car can we take? So some by the numbers. Which is the most popular car here? Volkswagen, BMW. So the BMW is most popular, I guess. So we need to some same year type of model. Let me see, where can I find some models? Oh, models, great. Okay, let's take some kind of series number. Can we have something similar? So I don't know, 320s, I guess those are kind of common. So we maybe also the years, because if it's like crazy different year, then also not cool. So let's say, so we have really old cars in Latvia, which is the reality. So let's take so from, I don't know, well, I don't want to take new cars, they're overpriced. So I don't know, like something like that. Well, it's still very expensive, but cool. At least we have some range here. So what I want to do, I want to have as an input, let's say the year, the run. So this is all the same type of model. And then let's predict the price. We could also add many other parameters. There's, let's say, there should be, at least there's no parameters here, but basically usually there's, whoa, I didn't know there exists 8-speed automatic, right? So basically you can add also, so this is pickup, okay. Yeah, so you can add all sorts of those parameters. We'll do this now, just in a second. So how we could do this? Okay, thanks for another like. So the Moodle. So please go to the Moodle. I will add a template, and remember we had this forward kinematics and inverse kinematics. So let's try to do this model in forward pass. It's called forward pass. And I have a template for that and equation for that, and we'll try to do this. And I believe that if you did the homework and you tried to do this last time, then this time you will succeed, hopefully. Last time when I was in Ventspils location, people did not succeed, but they did not give up as well. So this is great. If you not give up, you will succeed. So I guarantee you, those people who are working on these things for years on equations, this is again something maybe you just missed last time I told you, is that the deep learning, machine learning is super exciting, and at the same time, oh right, I actually have data. Okay, ignore data, the picture, just use the model and template. So what I'm trying to tell is that the papers are written in arbitrary way. Basically, any researcher writes the equations as they want. Even last time I showed you the derivatives have at least 3 forms to writing them. And basically, this is really hard for some people to grasp. They have learned like calculus in high school and university, and they say you write it in this way only, but in deep learning, everybody writes it crazy ways they want. And the only way how you be able to read these papers, if you just like struggle for a year and keep reading them, and at some point you start getting the point how to read them. So don't worry if it seems to be confused, just keep pushing and you will be successful here. So again, so I will put this on the Jamboard, Whiteboard. So Whiteboard, and also I put this in the Moodle, and I also know that some people are requesting the stuff or these tasks online, so I could start posting this in the chat and in the notes as well. So let me see, I'll post this in the chat. Great. Oh, 4 likes, thank you. Okay, YouTube don't want me to post stuff. Let me try again. So otherwise somebody will need to use OCR or ChatGPT or whatever to recover my text. Okay, template is shared. Okay, template is shared. If you have trouble getting in the Moodle, at least template is in the chat. So that's good. Okay, great. Let's try to do this together. I will open also in my Python. So this is 4.6. 4.6. Just a second. I need to make a copy of code. I don't want to mess up all of my stuff here. Yeah, I also recommend you please please try to make, oh, where is the lost? So please try to make that your code that you submit is not a named template. Please make it like live or whatever, like coursework, whatever. So so the template file stays the same, and then you change the changes. Okay, so good. Let me share the code. Okay, cool. So this is my, okay, something is not there, what I wanted. This is the previous code. PyCharm, where are you? Here. Okay, cool. So I believe this is kind of very straightforward. Okay, the absolute error as well. Right. Let me share the actually there is all of the equations already available. I don't ask you to do any kind of derivatives here. Let's make it very simple. Let's try to make it work. So let's the first iteration. So there would be here in the top part, this would be the year. So this is a year made. So just for this to work better, I think you could just normalize it by minus 2000, right? Or maybe minus 2010, whatever. And this, just to make it better, just divided by 1000, this will be the price. So something like that. I mean, like if it's created in 2015, you would just write 5, and then the next car would be, let's say 2020, then it will write 10, something like that. If it's clear, hopefully clear. Maybe we should use 2000, somebody will be confused. But again, you will get it more and more, but the idea is that for artificial neural networks, it's always super important to normalize, standardize inputs, outputs. So basically, this is like the rudimentary, very dumb way to attempt to do this. There's much better ways, which we will do later. So, okay, let me share again. Please, those who understand what we need to be done, start doing it. We'll see who did it first. And Then if nobody is able to do it, then I will help. Here is the equations. So the model, again, all of the AI models are not really algorithms, they're just equations coming each other, right? And here's the equation. So we have linear equation, sigmoid equation, we have our mean absolute error equation, and that's about it. So please implement it. If anything is not clear, let me know in the chat or here in the person, and then I will show you how to do this if it's too difficult for you. But forward pass is definitely not difficult, so please do that. So I will wait a little bit and see in the Moodle if somebody submits work, and who will be the first one, we'll see. So. Yeah, if not something clear, write in the chat. So let me write in the chat just to verify everybody is on the same page. Do you understand what needs to be done? If minus, then maybe ask a little, write what is not clear, then I can explain. So. Again, you take the cars either from the quote-unquote data set of the picture which I gave you, or from your own data here, right? Maybe really don't care that much about data as long as it's similar. So if somebody is trying to sell car for 100,000 at 2013, so that would not be a good data sample. We would call this as an outliner, or like a stupid person trying to sell old car for 100,000. So, okay, great. I see a couple of pluses, so we are good path. So, okay, nobody yet submitted it. Let's wait a little bit. Nobody yet submitted. And if you implement it right, if you run it, there should not be error, right? So you could try to even run it. Even if it doesn't work for you for some reason, you cannot fix the error, you can just submit it, we can look at it together. Nobody submitted. You can use Numpy functions. Please try not to use the some kind of completely ready-made absolute error. The some kind of, what was it, SciPy, the Lina, so norm functions like L2 norm, L1 norm. Please don't use those. Try to do yourself, probably, hopefully not using the assistance. But okay, so here the one thing maybe could be confusing if something doesn't work for you is that so as long as we're working just with one feature of the year, so let me add some data here and some examples just for you to get it going. So first of all, let's add some samples of data. So right, so there would be a couple of cars. Okay, I will just write the whole year so it would not be confusing. So 2012 made, the price is the 9950. Okay, then the next car, 2013. And the price would be respectively 7 to 1. So this is maybe not optimal because this price goes down, right? So, but okay, that's the life. So 2014, then this would be 1170. Then, but we could actually also, maybe the year is not perfect because probably the odometer is better indicator, but still. So let's take some even newer car. Okay, great. So then even newer car. So 2015, there is one, 2015, and somebody is selling it for 1249, like that. Okay, good. So something like that. So this ignore basically at this moment the normalization parts, right? So then we initialize the weights either by zeros or by some random value, but biases are always zeros. So then the linear part, again, usually like the last time we worked with matrix multiplications, we'll definitely work with matrix multiplications in the future, but for the sake of making this super dumb simple, let's work with simple multiplication. So wx plus b. So because each so there is a trick here, and this will come later, very important. So if I add here the matrix multiplication, I might shoot myself in the foot, because as long as, like, if I would have some kind of hidden representation of some, let's say, you don't write this, but basically if I write here zeros of some, I don't know, like the input feature is 1, the output features would be 4, and if I apply this equation, it would probably include in the two-dimensional matrix dot product all of these features. So this would be a very stupid thing to do, to make model that is dependent on the all samples. This doesn't make sense at all. So in this case, if we have just one feature, and remember that dot product is two-dimensional algorithm, so let's keep it like that. But then, if you have enough time, hopefully we'll do have enough time, like we'll show you how to do this with 2 dimensions. And from now on, then we will always use 2 dimensions, 3 dimensions, 5 dimensions, whatever. So, but just in 1 dimension, this is that. So far I already gave you this part. Let me see if we have somebody submitted something. Nobody submitted anything. Is it, do you need more time to do this? Let's see. Tev ir skaidrs, kas jādara?
Apmēram, jā.
Okay, nu pamēģini ieimplementēt, es tev palīdzēju kaut ko nokomentēt.
Jā, es tagad, es biju savādāk.
Jā, nē, fine, nu labi, tas izstāsta normāli, viss normāli.
Tad es tīri.
Ej, normāli, vai tā implementē tos rezultātus vienkārši.
Jā.
So, nu tu pāēji palaist, un ja tev kaut kas neies, pienāks palīdzēšu, un tad visiem būs skaidrāks, kas notiek.
Tas mēs to definējam tāpat kā...
So the viss ir tikai forward, te nav nekāds backward. Šeit, so here in this place we would write the same as in the equation. So let me go to equation, see what is need to be done. So there is a sum there. So it could be sum, it can be the average. So the difference between sum and average is that the sum is dependent on the alpha learning rate, and mean is not dependent. So in general, always use mean, not sum, but here is written sum. So sum is not wrong, but then you will need to have always, when you train model, to find different alpha learning rate, the step size, because if I have like larger sum, so basically if I have more samples in the batch, it will be larger, so this will be funny. Anyway, so yeah, this is what we need. So that's that. And hopefully the other parts are clear, like for example in the model itself, this is again very simple. So x, hopefully I turned off this guy, right? Yes, so these things like that. No, right, x is not that, x is that. And already we'll start seeing something interesting. So if I would add here a breakpoint, I would see that we have a vector of 4 predictions basically. So the model will be executed in parallel for all samples. So this is the way how Numpy works, and so this is already something you need to get hold of. So nobody yet submitted anything. If any problems, questions, I can help. Please write something in the chat so I can help. Otherwise, says looking at how are you doing, and then we'll see. So at least I have one reference point here. Vai kaut kā palīdzēt?
Jā, es to losu laikam līdz galam.
No, tev jāsauc losu funkcija vienkārši.
Jā.
Nē, jāpakaļ. Pirmkārt, modeli tā nevar izsaukt. Tas ir funkcijas izsaukums. Nē, apaļā iekau. tad padod iekšā inputs, tad nākamais ir loss, ir tagad arī funkcijas izsaukums loss mean error, yes, padod inputs. Tad pamēģini palaist, vai tev vispār strādā, viss, vai tur nav kāds bugs, ir bugs. So Sigmoid, positional one argument, many arguments given. So tev vajag linear outputu, sanāk, tas kaut iekava nepareizā vietā. So šito pēdējo iekavu jāpārvieto ir pirms dzēs mūsu pēdējo iekavu, jāvelc viņu linear outputs iet iekšā Sigmoidā, bet varbūt ir viena opcija, kā tu vari to samazināt, ja tu sataisīt temporary mainīgos. Zin, pirms komata jāieliek.
Pirms komata?
Nē, jau pirms tā komata. Jā, tā run. Vai vēlreiz run. Okay, kind of works, but of course, protams, viņš nestrādā pareizi. Es dzirdu tev, kāpēc tev bija mīnusā loss, kāds ir iespējams. Jā, tev tas nav pareizā implementācija. Tur ir absolūtā vērtība. MP, ABS jābūt pirms savu. Nu, iekšpusē samā. Tā. Okay, let's look if somebody submitted anything. If no, I will help. At least people in the classroom managed to do this. Okay. Let me help you out here because at least Thomas managed to do this here. Right, and then we'll get with others. So okay, so the sigmoid, how the sigmoid looks like 1 divided over. So don't forget the bracket, 1 plus np exponent of the x minus x. So then the linear layer, again, somebody had the issues with the brackets. So again, to avoid problems with the brackets and to make it easier to debug, maybe it's easier always to do something like that. So the layer 1 means the linear of the x comma w1 b1. And then it goes to layer 2, which is the sigmoid of L1, and then L3, layer 3 is the linear of L2, comma W. So instead of spaghetti code, the something like that. So this kind of makes it easier to debug. And of course, I did it here. Again, better would be to have some kind of loss value variable, and then loss absolute error, and if it's right, this is my own bad, I gave you the wrong stuff here, so there should be ABS around it, right? And okay, so here the stuff is there's a y prime, so this is not small y prime because this is the all data points at once, and then the ground truth, right? And there will be a couple of interesting things to observe here, so let's try to maybe observe them. So if I run it, so it works. So initially, the predicted car price is 0. Everything is wrong, right? But to notice, so first of all, this model, which is the equation for each of the cars, is now repeated 4 times here. So this is one interesting aspect to observe. Another aspect is that the loss value, because of the sum here, is the total loss of my data set. In this case, the 4 samples is my data set. So if I learned my data set perfectly, it will be 0. And this will not be for each sample, but for whole data set. And in deep learning and machine learning, you will see more, we always try to look at either the whole data set or the partitions, batches, because especially for image data, it's very hard to load all data set in the GPU memory. So we split it by, let's say, we could split this also by batches. So there could be 2 samples first, then 2 samples second, and then calculate loss from each of the batches. So that would be one way to do this. But in this case, let's look at whole data set. So this is the task number 1. Maybe I should put some of this to Jamboard, to Whiteboard. Unfortunately, nobody managed to do this quick enough. Let's keep hoping that in the future somebody will start making these things a little bit faster. normally in these courses there are at least some part of students who are able to do this fast enough, so you have room for improvement, you have chance to improve, right? So but don't worry if it's difficult at this moment. So so this would be the second part of the task, right? I put this, oh, okay, I'm sharing this on the whiteboard. So I put this here. Okay, let's move on to the next task. The next task, of course, is to implement the model training, right? And this will be using the partial derivatives and SGD, stochastic gradient descent. And we'll show this step by step. Oh, right, something is wrong. Maybe somebody, I like that somebody is, so you are like my natural intelligence assistant, right? So if I do something stupid, you find it. So should it be W? So def, I don't get it, what this meant in the chat. W1, B2, W1, or maybe did I did it in the wrong order? Let me see. Maybe I did it. So no, the W1 is by the X. I don't see the point there. If anyone else can confirm whether I have the bug, you could tell me. Otherwise, okay, you think the order, maybe the order is wrong. Yes, thank you, excellent. That's why I'm saying this is great that somebody is looking at my code while I'm typing. So thank you, I found my bug. You're absolutely right. If I would try to train this, then I would find it myself, but the problem is here that either I should change it here, or I need to change the order here, which is that X should go here and L2 should go here. Thank you, this is excellent. I really liked it that you follow the progress here and make corrections. This is right. So I will put this in the Jamboard for people to notice, I mean the whiteboard. So I don't have enough time to fix the previous one. I'll just add in the 8th slide. Okay, excellent, excellent job for the people checking me. Always, Ivis, thank you, excellent. So that's great. So let's keep moving. Okay, so I start telling about the training process. So this will be going here, and so the training process will involve stochastic gradient descent, and let me put some pictures and equations up, and then we'll, oh, this is not what I wanted. Then we'll understand what we need to do. Okay, so maybe you remember this equation, these pictures last time. So one is mean absolute error, another one is mean squared error, mean squared error. And what is depicted here is that I have a model that is being trained from 0 state, right? And initially it has a huge error in both cases. And then each iteration, and what is the iteration? Let me remind you, what is the iteration? It is the same iteration as in inverse kinematics. So, and the same equation works for deep learning, for basically machine, like these neural networks. So, and let me find, where is it? If I will not find, I will write it myself again, but I did find it, I believe. So, so the training process looks basically this, where was my chart? Yep, so this is the training process. I have my loss functions. I have the derivatives with regards to B1, B2, or it could be W1, W2, all of the parameters that can be changed. By the way, there is one thing that students do not realize. You can train also with regards to X, basically change the input. You probably don't want to do this for the car price prediction, but you might want to do this for style transfer, for example. If you want to have image that have the target output is like Picasso, and then I have a picture, and then I can transfer the style on my image. So this is possible to do with these methods. So this is what we need, and here this is the stochastic gradient descent, basically SGD, and this is also visualized on top with that picture. So what it happens? So these points means the like sum or mean value of the loss function, and it goes down, 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 and then basically again I could ask my question here. So okay, let me see. So here maybe this would be a nicer way to ask. So imagine if we are located now here, right, and then my question is, will the next loss iteration go most likely there, or most likely there? So no, let me see. So this would be a position, where? So this will be up, right? Let's write not a, but up. Oh, this is so annoying. I liked the Jamboard better, but now it's gone. So down. So up, down. So my question in the chat, let me write, so will the next XGD go up or down? So please write in the chat the response. You could also, you don't have chat, but you can tell me where do you think. Okay. Okay, let's wait for somebody to respond. So we can have a little bit of discussion if necessary. But this we talked this a bit last time. Again, this time the same procedure, same mathematics goes for training model. And this is the procedure. The question is up or down. Nobody answers me in the chat, kind of easy. Okay, we have one up. Other ideas? Other ideas, please, 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 right? Again, I will not call by name if somebody do something stupid in the chat. Please just write so I know if I need to talk more about these things. Otherwise, they'll just become harder and harder, and then if you don't understand what you're doing, it will become impossibly hard. So anyway, so we have 2 up, 2 down, and that's interesting. More ideas? Okay, by the way, this will be a great example because you will be able to, in just in a second, do this in Python and see the right answer yourself. And this is the mathematical answer, not my answer, right? So I've heard some crazy things going on in some Western countries where you can think of your own mathematical answers. Here we have just the answer that is produced by mathematical law. So there will not be option of debate if it goes up or down, but but again, don't feel bad if you missed it. Like if you don't give up, you will be very good at this very soon. So 4.3 task, I'm adding that in the Moodle. Please take that template. There is another template. We will kind of extend our existing template with that one. Please take that one as well, because you can just copy a couple of things from that other template basically. So please take another template, and meanwhile I'm waiting for the answers. Maybe somebody wants to explain as well their answer, because we have kind of 50-50, which is I think good because people are thinking about it rather than just using some assistance. So okay, so do you want to tell me why it goes down? Jā, vienalga tur pateikt, kā to vērtē.
Jā, manuprāt, tas, ka viņš ar to pēdējo aizgāja virs augstāku viegli.
Yeah, so in the classroom, like intuitively, people are telling that it will go down, and this is actually correct. So, but the reason why it is correct, so I think we all understand that 0 is perfect, right? So the loss functions tend to go to 0 always. But then what happens here? So if we look back in the previous step, basically the previous step we were here, and in the previous step the mean absolute error, all of these steps here, these are alphas, or if you look at here, so this is the alphas, right? So these are these guys. So the steps, and this is constant size, and it overshoot itself basically and went to the other side. So the next time when I go from here, remember that the derivative or this d or delta or grad or whatever, it always shows towards the basically towards either the maximum or the minimum. In this case, because there is minus sign here, it means that it will always show to the minimum. If I put plus sign, it will show to the other side. So, and this means that from any point, it will always point here down, 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 down. And if I'm on that side, there is absolutely no way it will point in that direction. It will always point down as long as I have minus here. So intuitively, what you need to understand is that optimizing loss function, SGD, is always, and you see minus here, it will always point to the minima of the function. If I have plus sign for the generative adversarial networks, then it could have the opposite direction as well. But I would say like in 99% time, if you have optimization and this is minimization, it will always point down. And in this case, what could happen really is that this guy could jump on this side here, right? This could happen, but it could not happen that it goes there, okay? So this is the intuition. And then also there are cool stuff happening. So if I'm using now the mean square or mean absolute error, so, and I have cars, and if I have some car where some guy is put that this car costs like $1 million, even though it's old car, then it will produce a huge error, right? And if you see here, there is E8, right? So this is, so it's like 100 million, I guess. So 100 million error units. So loss value. So this is very high gradient. And it means that if you see that this arrow or this lambda or like alpha, this multiplication is really a large step. And when it goes further here, it's small step. But if in the other batch here, if I'm like trained my model and went close to the 0, and I get this outliner will move me again. It will try to go maybe here, but it will over jump and go somewhere here, very far away. But with absolute error, it's always constant. So what I'm trying to tell you, if you have noisy data where there is outliners, some strange data points, then absolute error is way, way stable than squared error. But if you have very clean data, the squared error is perfect. So it already you start seeing that if you understand what you're doing, it's completely different game. But basically, if you're just taking GitHub repo and press train, you're not understanding anything basically. So, and this is not just the. This is just like the scratch of the thing. So we'll have much more interesting examples. So hopefully this is, so if it's based on the mean value, then the previous values, the mean value. So this is the mean value of the whole batch or the whole data set, if that makes sense. You will see this just in a second. Anyways, like even if you answered wrong, it doesn't mean that you know, you just keep fighting and you will understand how this works. So okay, let's turn now to solving these equations and then coding them, and then you will have your first neural network model, and then let's see how much time we have and how far we can get. So I guess probably because of the time limitations, I will not do all of the variations in very high detail, but at least I want to do some in very good groups, like groups that are capable. I always like give these derivations also for students to do, but at least here we could, you know, work a little bit together. So so let's take some concrete examples. So I had these B's stuff. So where's my B? With regards to the B, where did you went? I had this somewhere copied and then I lost it. I don't want to write it again. Okay, I found, ooh, there's a lot of equations. So, okay, we'll take some of this stuff. Okay, yeah, LaTeX, yeah, right. So with regards to B1, And I believe I'm missing the loss function. So there's the loss function. All right. L. I have it. Right. So I have the loss function as well. We'll have a little bit of latexing. Loss function. I believe I have all of the elements here, so I need to calculate this guy, right? So how can I do this? Again, this is the chain rule, and just for you to understand what it actually means is that I can rewrite the same equation in very awful manner, but then this would make sense, hopefully, to you. So nobody usually writes it in that way, but this is what it is. So if I write it in that, so this is actually what it is. So this is onion. So this is how you must look at all of the derivation problems, as an onion with layers. So there is a function layers, and you start from the outer layer and you go into deeper layer as long as you find B1, right? Everywhere where there is no B1, I don't care about that. But again, if it's a layer, then this, what I mean, don't care about it. It's you just multiply it by the inner derivation of the input. So the chain rule. So again, we will not go in super high detail here. Probably it will take very long time, but at least I will try to do a little bit of that. So how to decompose this? The wrong way is to open the brackets. This is not the right way. Open brackets, this is the high school physics, which results in unsolvable huge equations, which is not the way how deep learning models can be implemented. But the way how to do this is using the derivation rules and basically the chain rule specifically. So, and again, this is something for people to remember, because often they kind of get confused, is that anything that we will do now, all of this is just numbers. Basically, if I have different sample of car, it will be completely different numbers. It isn't the answer of these models is not the equation itself. Equation is like a template. Basically, the answer is the trained price prediction. So, and this is not like high school physics where you have the answer, just the formula itself. It is not like that. So, how to do this? So, you would have the first guy derived by the inner part of this output. So this will be a number, basically. So all of this stuff will be a number, and this number is then multiplied by another number, which is c dot, and probably I need to put it in another line because it will take long equations. So, and you notice here is the derivation sign in front. So the next one will be linear stuff of, and by the way, I guess the B1 is the kind of nasty because I need to go very deep in the onion. B2 is simpler equation to derive. So so let's see. So but let's anyway show it. So here will be linear sigma. Right, hopefully I did not miss something. I don't, right. So sigma. Okay, so see, there is not the equal sign, but multiplication sign at the end. So you do that, then again a multiplication, and you just like layer out all of these onion layers till you get your target variable. And to get these, so basically when you have this nice equation, when everything is laid out, then you calculate derivatives of each subpart, and then you put it all together just like a Lego. So it is not actually that complicated as once you start doing it. Initially, it might seem very complicated. So now sigma, and we do this so long as we get to our target variable. For B2, we don't need to go as deep. Basically, for B2, it's simpler. For B2, it is simpler. Maybe we should actually derive B2 also. If you do this on the paper, it's also probably simpler, but still LaTeX very cool. Need to know how to do this. So sigma linear And also keep in mind that so this is the whole equation. So keep in mind that these linear sigmas whatever loss mean absolute error, all of those guys are basically what they are. They are equations themselves. So we can just open also them. So the last thing here, which I wrote from linear like that, what it actually is just W1 times C dot X plus B, right? So we could write it as a linear, or we could write it as that. That is the same thing. So it's just so that you don't get confused, right? So that's that. So this is the whole derivation of B1 from the loss function. And if I have this whole answer in numerical format, I can plug it in that equation, run it in the loop exactly the same way as for the robot arm, and I will get it trained so that it will predict the correct car price. So, we'll move on with this more. If you have any questions about this, write in the chat. I will look at this. I'm now putting this on the slide 10. And let me focus more on B2 because I just realized that B1 is long equation. So B2 will be simpler. So let's switch to B2. B2 is so in the programming terms, I don't care because, you know, just call a function. That's easy. But if I wanted to write it with the hand, this is not as easy. So B2. So this, and the good news is that's easy to change because B2, it basically what it means is I will just cut a little bit of stuff. So I don't care about this guy. This I don't care. There is no B2. There is no B2. Right. Yeah. Wait. There is somewhere. There is. Where is the B2? Okay, B2 is okay, linear. Okay, B2 is here. So okay, excellent. So I cut a lot of stuff down. See, so it will be just here. So I put it on the whiteboard, the previous equation, and this equation looks much nicer. So I have just I have basically just the loss function derivative, and then I have linear derivative. Even don't have sigmoid derivative. Sigmoid output, so the output of the sigmoid and linear goes as an input to that linear layer. That's it. So I treat this guy basically. I treat, where is it? So I treat this guy as just an x basically. So it is as simple as that. So basically, so this will be good. So this is what we are targeting to solve, and if we solve this, we can solve the whole model. Any part of the model will be solvable if we understand these principles. So how to understand this? So this will go to slide 11. Slide 11. So we should decompose, and what I mean by decompose is let's calculate derivative of each function part separately. So, for example, derivative of the loss function, and we could write it as we want. So let me, well, just a second. Wait, it's not copying. I don't want to write everything by hand. If I will, then I will write it, but come on, why it's... Okay, now it started to copy. Okay, hopefully I didn't delete anything. So, okay, so I need to do this. And actually I could maybe find some description of that. Okay, so, okay, again, the same way as last time, we can just drop the sum mean. That's just will not change. So, because the sum and mean will not change because the sum of things is basically of the same equation. Sum is so we'll derive it the same way. Like if I derive the same equation n times, this is the same derivation n times. So I don't care about that at all. So minus y. So that's just repeated derivation. Sum is repeated derivation, so I drop it. But if I want, I could just leave here sum, and this will just keep going on. Like sum mean, this will just be repeated. But for the sake, just let's remove that. So how to do this? If you look at this the first time, you might be extremely confused because you don't see any derivation rule that supports this stuff. But if you think about it a little bit harder, you might notice that you can do absolute valid variable with some mathematical tricks. Like for example, the simplest mathematical trick how to do would be to add sqrt, like that, right? And as soon as we start doing this stuff, so this is the absolute value, right? So maybe there's some probably maybe you can think of some other trick to do this, but this is the typical way how to do this. So and then what else? The square bracket also seems strange. For if you look at derivation rules, there's no square stuff here. So but square is actually also something that we can rewrite. So the square is actually, if you rewrite as 1 over, okay, let's see, frac, this will be disastrous. So from over 2, so, okay, cool. This is squared. So now it should start looking something more derivable, right? So actually, maybe it's difficult for you to see if you're not familiar with this, but this is again onion. Basically, dy is inside the onion. Again, you have right way and wrong way to do this. Wrong way is to open the equation up there. The right way is to decompose with the chain rule, right? So what else we could do? So to make it not as painful as it looks, let's rewrite it a little bit. So so just for my own sanity, what we could do here is to add here. So let's make that this is letter like the y prime minus y is a, basically. Let's do that. So if somebody now looking at this, what is a? So let's put a as well here, ay. So this is a, right? If I have a like that, then I can write it much more friendly manner. So let me think. So if I would like to derive it by a first of all, okay. So I will maybe copy one of my equations. Otherwise, it will take very long for me to write it here. If I would be able to copy it. Seriously, again, starts doing this stuff. So okay, cool. So this would be that a stuff. So what I do here, the first step, split it onion. Here what I do in the first step is use the power rule to move the power to the front. 1 divided by 2 minus 1. So that's that part. And the second part, I'm accessing the middle part of the onion directly and doing the same thing with the power rule, right? So in the power 2 minus 1 is 1 and then becomes a. So then I'm making this equation like finishing this equation. And then I'm seeing something like this, and then I'm seeing actually that the bottom part is the same way as it started, and then it basically means that a divided by absolute value, plus also I'm adding here epsilon for numerical stability. So epsilon usually is e minus 8, which is the smallest floating point 16-bit number, I think. So you could do also in different ways. Like you could have epsilon added to the both parts, like top and bottom. There is no like specific rules how to do it, but I don't want to divide by 0, right? So this is what I'm trying to avoid. So this is actually the derivative of that, right? So and then if I add here in the a y prime minus y, and there is y prime minus y, this is the final product that I'm targeting basically here. So I already have the one Lego piece ready. So the middle part, so this last equation which I'm now highlighting, is solved. Then we have the linear layer, and I believe the linear layer is so simple that you should be able to do this yourself. And we already talked about this last time, I believe. So the linear layer equations looks something like this. Where is my equations? Of course, you did not work now. Okay. Okay, let me just delete all this stuff. Hopefully I will not need it again. We'll see. Okay, so this is very simple. So we have this great opportunity for you to try out. So what is derivative for the first?
W
So with regards to W, what is derivative? So how we do this is this. So with regards to W, it is, so we look at our variables. Where do we have the target variable? So it means that W is our target variable. So this will be 1 minus 1, and the multiplied part stays there because it is like, you can imagine, like a constant, right? And this other guy B is definitely not related to W, so this becomes 0, right? And then the output is basically Y, right? So if I look at this, it should look like that. So that is output, right? And then for the X, what is the output? W, yeah, the output is W. And then for the B, what is output?
X times W?
No, think about it. B. So the B is our target variable. We're looking at. So the plus is separating stuff, and if I'm plus something which it's not related to B, it becomes 0.
Yeah, so B.
No, think about it.
No, really?
Okay, so the first part becomes 0. The second part is containing B, yes, but we are applying still the power rule, and there is a 1 minus 1, and then it becomes 1. Okay, so this is what we have here. Okay, so that's that. So I hopefully you understand the direction. I will start to help you right in getting. So by the way, if somebody is like difficult getting this, there are two ways. One way is just keep fighting and you will understand. Another way is I'm trying to post all of the in the materials, all sorts of videos and other people presentations and code. You can go in and learn yourself a little bit more, but just this will come natural to you. It is not as complicated as you think. It's actually very, very easy. So let me give you some Lego pieces here, and then I will try to put them together. So the simplest possible Lego piece which any of you must be able to do at any point of the day is these guys. So these are linear layers. This is like, I don't know, like simplest as it gets, like nothing. The derivatives are really dumb. So then, and the funny thing is actually this is the main equations for all of the models, even transformers, ChatGPT, whatever. So, but then the other, which is a little bit more complicated, is the absolute error derivative, which maybe I could rewrite for you. Okay, let's rewrite it in a very simple terms. I will give you all of the pieces, and then we will able to do this very easily. So let me give you the derivative nicely here. So wait, I have it. So it is not difficult. So right, again, not copying my equation. So I have one plugin in my computer which is really nice, but it's preventing me to copy stuff. So paste. Come on, just and I don't want to rewrite every single thing with hand. So okay, let's write it here. So again, y. So again, the order is very important, but here in this case, it depends on my order how I place things here, but basically don't mess up order. So if you have here the order y prime minus y, then definitely you must have the same order in the here with the derivative. If you, so the absolute value will not change, but the derivative definitely will change. So so that's that. And let me show you how it looks like. So there will be a frac of this guy divided by the was it yeah, was it without this? Oh, that's why you need to have order. Otherwise, it will be terrible. So epsilon is just e minus a. So like that. Okay, so this. Ooh, what are those crosses? How this happen? A mathcal. Right, I know how this happen. Mathcal. There, I don't need to have mathcal here. Okay, this is the absolute error. Okay, cool. All right, there's still some stuff going on. Okay. So now it will be, yes. This is the derivation of the loss function. So I'm putting this also on the Jamboard, the whiteboard. So this is Lego piece number 2. And then the last Lego piece to put all of this stuff together is the derivation of the sigmoid itself. I could show you the whole derivation, but maybe I could find a finished one. Okay, let me just, so discard image, let me just give you all of that stuff. So, oh man, how little slow it is. Okay, so this is the last piece. So the sigmoid, so the derivation with regards to x, by the way, this is also kind of fun because learnable parameters are WB, right? Those are changing. Sometimes x we want to change, but almost never we want to change x. So in here, the sigmoid do not have learnable parameters. Sigmoid is just like a transitionary function which pass the gradient of x which coming in just to the next function. So it is not learning anything. So the main signal where to go in our training process is received from this guy, absolute error. Then it's passed through the learnable stuff in the linear layers, then here, and then again here. So it is that way how it's structured. So then, yeah. Yeah, you can use different non-linearities. Definitely in the homework, maybe I can give you some other non-linearities, but it's again they also sometimes called activation functions. We'll maybe look at these metaphors of neural networks later, but activation function research is not something somebody should attempt to do because that's meaningless. So like a lot of people have tried to do different kind of activation stuff. They never succeed on anything good because basically, so in a brief words, the activation function research is so they found that ReLU or Sigmoid or whatever always works, so you don't need to have anything else. So it's pointless. I have seen research on that. So okay, let me show some other part of this stuff. So I already gave you the template. Please get the template ready. We'll start coding just a second. So this is the other part of the stuff, and let me color code maybe maybe let's go here. Color code some things so do you visually see what I'm trying to do here. So this is the car price prediction. So the Y prim here, this is the car price prediction. This is the error, how bad is our model, right? And to train this, we need to do this SGD stuff. SGD is here, right? The B minus or W minus or this. So we need to have this guy. And this guy is the gradient. It's called, if we have a matrix of multiple features, this will be Jacobian matrix. So here we have it also here. So this guy, for example. So this is the very important. This is very important. Yeah, these two are very important. So if I have these things, then I can calculate how should I change W1 so that my model gets better, right? So if I have these things, then I can change W1 so the model gets better. So how do I change it? Again, let me add another equation, otherwise somebody might get confused. I don't want you to get confused with this because this is not difficult. Even though it looks difficult, it is not difficult. We will also see this in the code. So so this is SGD process, which is repeated many times. I will add it here. So this is what we want to achieve. So this is the training of our neural network. So this part is the training part. And to achieve the training, I need that particular variable, right? So let me delete it here. So let's start the color coding stuff. So I need this guy. This is the constant, but I need this guy. So and how can I get this guy? So and now it's just basically Lego. So I need this one, and this is here. So I plug it in. That's it. I need this guy, and this is located up in the right corner. So with the regards to, so this is this, right? So I'm plugging in there. If I put the right numbers in, plug the equations in, put all it together, I have a training process ready. That's it. So let's keep color coding stuff. So here is the linear layer. Here is, so this is with regards to W1. So where do you have? So again, so linear, here is the linear yellow one. Where is, well, okay, by the way, the final output is down here for, so to get this W1 stuff, so the final output is in the bottom part. So there is the linear, so here's the W with regards to W. So this is yellow. So the, oh, right, there is also interesting stuff. Oh no, we have X. So let me, orange one. So this is with regards to X, and this gets maybe confusing, but if you look here, this is kind of important stuff. So on this equation, the X itself is the output from previous layers, see? And with regards to the previous layers here. So that's why we need also linear with regards to X. Linear with regards to X is the transitionary state in between the layers. And this is the same stuff also going on with the sigmoid. So sigmoid is here, and here's the answer for that. All right, again, I used the same color, sorry. Different color, blue color here. So this. And the green one, I already have it here. So for W1 also, all of the colors are available, right? So just place in the right order. Okay, so now let's try to do this in the code. I gave you the template. I need to get my template ready myself. Where is the template? So let me find it quickly. Regression forward, so that's definitely not what I need. Regression by hand. Wait, I will find it. Okay, I will just download it, I guess. So simpler. So okay, let me quickly get it ready. So 24 live. Live. So I'm just copying it back to my. Okay, this is wrong location. Second. Regression by hand. Live. I don't know, like, I guess this will be that one. Okay, cool. So we have all of the templates for functions. Everything that we need is here. So how to do this? So I'm copying stuff from the previous template, X and Y, into here, chick, like that. Then I can also copy all of the forward functions, like these functions are the same. So linear, sigmoid, model, loss, mean, absolute error, whatever. I believe all of this can be copied like that. Now we have these derivatives, and derivatives, it's easy to do basically because derivative with regards linear with regards to W is X. With this one is 1. With this one is W. So with the sigmoid, we need to have that equation which I had on the whiteboard because I don't know it from top of my head. So this is the sigmoid, well, right, sigmoid of X multiplied by 1 minus sigmoid of X. So this is that derivative. Then y prim loss derivative that we also had. So this is, and here the order is super important, because here on the top part the order is important, and in the bottom part it's not important. ABS y prime minus o, and if I'm switching around order it will become worse, very bad. So plus 1 e minus a, that's for the stability to not divide by 0. 1 e minus 8 is the smallest floating point for 16 bits, I believe. Okay, so I'm adding this stuff to the whiteboard. This is the new part of the code. All of the previous code was already given to you. So that. And this will be the slide number 13. Okay, so this is given. And then starts the fun part here. What I believe I will do today, and then you will do yourself probably finished up. I will not give all of the equations to you. We'll give some of them so you get the feel how to do this, and then you can finish up yourself, because again, this is just stringing together pieces very slowly, very carefully. So okay, let's try with W2, because this is the simplest stuff. So again, let's see, we could do this step by step or at one go. Okay, I will just, I don't know, like, let's call it grad, because it is gradient. So here we'll have d d of this guy, y. So again, multiplication of the onion layers. So first onion layer, and the equation which I'm now referring to is given on the slide 12 with colors. So then the next one is dw of the linear layer, and the input of the linear layer is exactly like also in that slide. So there will be sigmoid. So actually, just not to mess up the order. So first one is x, first one is y actually. So the order is a little bit different than in my slide. So W2, I believe, should go there, B2. And now the x is sigmoid of linear of W1, B1, x. So this is literally the same equation that we had before. And I believe you should not have any problem of implementing B as well. And then for these other guys, it would have more multiplication parts. So again, we could just literally copy it here like that, and then change here just to dB. This is as simple as that. So okay, so these would be these two very simple guys. Okay, so adding this here. And by the way, till the end of the lecture, maybe I will show you a little bit how to do this with the multiple input features. We'll see. So, okay, so this is the model, this is our prediction, this is a loss, this is sum. I don't like, there's y, is, something is not right here, there should be large y. Oh, right, and this is super nice. DW1 lost, oh, right, but that's not implemented. DW2 is implemented. And also DW1B is implemented. And by the way, we also will have a great opportunity to observe that these models work magically, sort to say, even if I don't implement all layers. So, but this is not optimal, of course. So, and then how to train this stuff is by W2. Remember, we do the minus, right? dW times learning rate or alpha. And the same for B. And now, the same way as for the robot arm, now in this case, and that's why I highly recommended people to do the robot arm properly with the derivatives, not with some hacky ways, because this is the same way with derivatives, how neural networks train. So, and here we will go, what is expected behavior in 1,000 epochs. An epoch means that I will look at whole data set 1,000 times. So this, no, epoch means each time of those 1,000 times. So we will get closer to the loss of zero and better prediction of our car predictor. And how this is actually, if somebody has a question, how then I will use this in the real life, is that when you will do the training later, you will save your weights, W1, W2, B1, B2, and then you can deploy this, this model in production. And in production, you will not use the derivatives at all. You will just use the forward pass, and you will have a great model predicting car prices without any kind of training. So this is the end game. So now I'm just making a screenshot of this, adding to the Jamboard, to the whiteboard, and we'll see if this works. It might not work, but we'll fix it then. So run. Okay, this is not the right code. Run. Okay, good. So it, oh right, it even plots the loss curve here. So the loss curve doesn't look excellent. It's really, really high numbers because there are high numbers over here. I could give you some small hacks just to make it work a little bit. So one super simple way how to do this, and we will do this more and more in the future. Let me just see which task I give you. So Numpy, a feature, model, matrix, weights, right? So I didn't show you that. So X, so let's do the standardization. Standardization is one of the simplest ways how to do this. So it will make all of our inputs and outputs around zero. So if I want to reverse standardization, then I should save those standardizing variables and then just repeat equation in opposite. So but of course, don't be scared that this will not look anymore as years and prices, okay? Because you can easily get back to that. So if I would save like how it's actually really be done is something like that, you could actually write this code because this will be useful for you. So divided by x std, and then to return back to the real values is easy to do, right? So and then I can do the same for y, and if I do this, then the loss curve will look much better because now it's a huge numbers, and normally no deep learning models work with just raw inputs. If you do this with raw inputs, you do it wrong. So so because the if you remember the sigmoid, it's at around the zero, and if you start feeding huge numbers, this is like wrong way to do this. So run. Okay, now it's dead, but it's dead. I think primarily because we don't have second layer learning. It's not too bad. I believe we could somehow, let's see what is the equation. So if I'm learning right now, so I'm not doing it wrong. So this is correct. Just bear with me. But I'm just looking at what we could do to revive it with what we have. The full solution would be to implement all of those forward passes. So those backward passes. So, and by the way, again, this is called forward pass. This is called backward pass. So, okay, so we're training right now W1, W2, right? So where it is in the graph. So this is here. So what happens here? So this is dead probably because X goes multiplied by 0 and then it's dead. So what we could do is we could just make the initial values of W's as ones, then it will not be dead at least. So if I run it, yeah, so now it's not dead, but now it's chaotic. So see, like it's 1,000 epochs running like crazy. So what else we could do? So I'm just changed these to initialize in different way. So what else we could do? So e minus 2, like we could just make it smaller learning rates. Let's see if that helps. Okay, now it looks better. E minus 2. Okay, now it looks good. So okay, like it's not perfect because we have really stupid model and really stupid data, but at least it works, right? So it is going in the right direction, and then it starts oscillating. The same thing that we showed with this triangle example, it's happening here. That absolute error is jumping around, right? So if you don't want it to jump around and you're sure that your data is clean, just use squared error. So these are some really dumb small hacks to make it work already. But to make it work properly, you in the home, you need to struggle through and be able to implement those two other functions, which is really not that difficult to implement. You just need to keep multiplying the Lego pieces and in the right order multiplying them, right? So I will add to the whiteboard also these few samples of what I just changed. And then till the ending, I want to give, like if you have just a little bit, like literally 5 minutes, I want to show one very important additional step, which I'm just wondering, should I show it? Because otherwise maybe it's too much information for you. Yeah, it's already too much information. Yeah. Okay. Okay. No, let's not show it. So, but in just to give a glimpse, next time we will not work with stupid models like this. Next time, what we will do, we'll have inputs of multidimensionality. There will be a car made 2012 that has driven 100 miles, 100 kilometers, right? That has had 4 owners, right? So we have 3-dimensional input, and this will be the truth for all of the inputs. And the outputs also can be multidimensional. So the outputs right now, so this will be like the input, and the output will be also always multidimensional. Even if it's one dimension, it will always be multidimensional. And why I'm showing this here and explaining this a little bit here is that then if we do that, then all of the multiplications will immediately become dot products. And you will need to be very careful following around dimensionality so that you don't mix 2 cars together in your model. So that always the dimensionality is multiplied by the last 2 dimensions for each sample. So, and for novices, it's very easy to, not understand this correctly and just, oh, this dot product works, run it, and it actually starts to learning what is the correlation or between this car and this car with this data and that data point. It doesn't make sense at all. So it must be able to calculate this dot product multiplication with weight matrix for each sample separately. But as you remember, that Numpy does operations in parallel. So it means that if I call this guy here, if it's correctly configured, and what I mean correctly configured, it probably means that you will need to have something like along lines, let me find, so something along lines like this. So there will be batch dimension, comma, so there is a batch feature dimension. So no, wait a second. So this is, so let me give you that example so that I don't mess up something. So there is a batch dimension is I have 2 samples in batch, then the feature dimension, yeah, so the feature dimension, and then I have mp new axis. So this is just, so what it actually does, it adds here additional square bracket like that, okay? So that mp new axis, what I just wrote, I highly recommend at home to play around with what I'm showing you, just a little bit to start getting what it is. So it adds another axis around here, and actually I would probably need to transpose, right? It depends on how the matrix is configured. And then at the end, I would remove that axis. And how I remove that axis is by selecting this dimension, and like taking that one off. And if I'm not doing this correctly, then I will be sometimes able to do dot product, but it will not be repeated for each dimension. That's why I'm always telling you, since we started working with dot products, that dot product is a mathematical operation or algorithm that works. This is basically algorithm that works on the last 2 dimensions. So if I'm not adding this new dimension, it will start working on these two dimensions which are here, and this will be nonsense. So basically, I need to add additional dimensions so that it works separately on each of those samples. And this first dimension is just repeated n times. So it will become much more clearer now. Last time, I'm just giving you this example just to start thinking about it. We'll make sure that in homework this is not absolutely required to do, but if you want to attempt this, I will be very happy. So, okay? So that's it for today. For the next week, I need to look at my calendar just a second. As I said, I will be in Dubai, and this will not be easy. So just a second. If I will not have any investor or business meetings on Wednesday, I will presumably put the same time around this time just remotely next week. If by any chance there will be investor meetings, then probably I will shift it some week later, but just follow, okay? Hopefully that's what we cover here is exciting. At least when I first found out all about this stuff, I was excited. This was many years ago. Hopefully you also can be, because again, in the very beginning, I said to you, you can study your thesis in master's, bachelor's, some kind of which library is faster, right? Or you can discover something new, and here you can discover something new. So that's it for today.